step along to the final chunk, or the second chunk, the big chunk of today, which is recapitulating the whole idea of the low carbon heating plant. And if I could offer to every single hospital on this call, whether you have a low carbon plant now, as in other words, you've got the technology already, as Milton District Hospital does and several others of the newer hospitals, or whether you're an older facility, the requirement to both know the carbon emissions, the kilograms per square foot coming off your facility, knowing what makes it up and how to bring it down, how to reduce that, is necessary. And we know that by 2050, Canada is committed to be net zero as part of the international climate agreements. And those are not notional ideas. Wouldn't it be nice if we could get to net zero? There's enough science. And part of that is look at the hurricane season this year. You know, it's kind of dwarfed a bit by COVID, but already we've got more letters of the alphabet used up on hurricanes than we've seen before. We know this is not going away. 2050, if anything, is too late to be net zero, and hospitals are going to be in the crosshairs. You're going to be at the forefront because you're clearly centers of community and large emitters. So over the next 10 or 15 years, we'll talk about this with heat recovery chillers in a moment, but you're all going to be transitioning over there, and folks like Multistack are going to sell a breathtaking number of these machines as we transition from heavy steam to hot water, condensing hot water, heat recovery as the path of the future. So that is why Greening Healthcare is investing so much with our friends and partners and sponsors into putting together a framework to allow every one of the hospitals on the call, every Greening Healthcare member hospital, to work their way over time down the path towards low carbon. So reminded you of this before, the roadmap idea. This applies to every building sector. There are 4 steps to zero carbon, if that's where we end up. One is energy efficiency, which is the least expensive, the highest returns. The second, which is getting least attention, but more so now, is heat recovery, recycling the heat that we throw away from the building every year. Then we need on-site renewables, then we need purchase credits. It's really that simple, but we can't get there immediately. We've got 30 years to get there, 20 years would be better. And every capital decision we make along the way is an opportunity to either move down that path or do a like for like, the things we've always done, and wind up with stranded assets within a few years. So the roadmap idea is fundamental to, we can't get to low carbon or zero carbon immediately, but we can get there over time. The notion then of, and this is an evolving model, which is why I show it to you again, I think you've all seen this, the elements of your low carbon pathway are the colored boxes in the top right hand corner. And what's been interesting recently has been chiller plant expansion, chiller plant replacement. So that's been added since you last saw this chart. And that when we install a chiller, it's an opportunity to think about, should this be a heat recovery chiller or just a conventional chiller? And it's different in every case. But as you will recall, the low carbon roadmap goes through the asset management system, gets you to the vision of the low carbon plant in future. That is what this is all about. And it's fundamentally different decision making than has happened before. It's a different process. It builds right into capital planning. And you guys have to be at the forefront of this. You have to lead that charge because only you have the knowledge to make this work. The other area we've been playing with, and we'll come back to this with Kitchener-Waterloo Hospital in a moment, is, again, you've seen this chart before, but we've added flue gas heat recovery. We can't find instances yet where technology is far enough along that we will not be burning natural gas or oil or consuming steam within hospitals in the foreseeable future. So we can work our way towards that of avoiding fossil fuels. But meanwhile, one of the areas that all these yellow lines are where we lose heat, exhaust air, we need to recover the heat from it. Local cooling units, local AC units on medical equipment, on kitchens, on morgues. We need to recover the heat that we throw away there right now. We need to improve our envelope heat loss when we replace windows and do building envelope work. But flue gas heat recovery is a big deal, and we'll touch in a moment on condensing heat recovery from flue gases, which is a flue-based technology that was significant 30 years ago, and we're not seeing as much of now. And we want to come into how that could fit together with a case study there. So this model of really stepping back and looking at your hospital and saying, where is all the heat? Where are we throwing heat away in the middle of winter now when the boilers are running heavily? These are the primary categories, and these are the kind of strategies you're going to be weaving in with your energy efficiency measures, with your opportunities to lower consumption, to reduce emissions, to reduce utility costs, but also to bring down loads so that everything becomes more manageable along the way. So this is the second step of the framework. And again, I'm not going to repeat all of these, but you recall that this is Grand River's Freeport site, which we profiled 2 webinars ago as an example of the low carbon roadmap builder. And this is the kind of chart we suggest that all of the hospitals are going to be developing over the coming months and years. We know that your building condition assessment is going to be an integral part of that. It's going to contribute essential information to make this all come to life. But you'll recall the procession here was the hot water boiler plant was considered to be the end of its rated life. Infrastructure renewal funding was allocated to the replacement. The consideration by the hospital was, do we do like for like, or do we look for low carbon options, which in this case were, can we bring the load down to have a much smaller right-sized plant? The pathway flowing out of that was to do non-destructive testing to buy time on the existing boilers. That's been done, and there's 10 years life left in those boilers, and the hospital is now looking at upgrading the burners and controls to make them as efficient as they can over the next 10 years. But meanwhile, we got time now to do the other load reduction things. So when those boilers get replaced, they're going to be much smaller, much more efficient plant than they would otherwise have been, likely including a heat recovery chiller. Then building condition assessment over time informs all of this, and the final stage, as you know, is what are those succession, those blobs, those circles on that chart, what are the succession of projects, which order should we implement them in, that leads us to the right situation 10 years from now when the plant likely will have to be replaced. Where do we get the money from, and how do we do the life cycle costing so we can present a sound business case to management? So this is the framework, and I'm going to beg your indulgence over time, because we will be bringing this back as more hospitals start down this path, as there are more stories to tell, and as the existing hospitals make more and more progress. But this is the pathway I would suggest respectfully every hospital on this call is going to be working their way down over the next 10 years, the next 20 years, so that by the time we get to 2050, we have what we're looking for, which is the least carbon hospital operations as part of this overall economic transformation. You'll recall, and then I'm going to pause again to see if you have any questions. This is a great time to ask them. When we presented this back on June the 24th, we ran a poll that said, what's going to get it? You know, if this is so logical, and nobody yet, I mean, you can use the Q&A now to tell us this is crazy if you like, but nobody yet has said that this doesn't make sense. So this seems to be the right path. What will get in the way of that? The biggest concern around capital funding. Well, guess what? There's going to be a one-time, in our view, bonanza of infrastructure money coming down the line over the next 2 or 3 years as part of the economic recovery. We got to be ready. Getting management and organizational buy-in was the second biggest issue. You've heard from our panelists today about how effectively they've been able to get everybody's heads together around, again, the business case, the technical issues, the adjustments that have to be made to make this work. The right equipment and services, we have an unprecedented number of industry players, consultants, equipment suppliers, service contractors on this call today, because they want to play their part to support the hospitals in working their way towards their end goals. Then lower down was, how do I actually put my own plan together and how do I get my own staff involved? So you see those results. We will re-poll later in 2021 to see how this has shifted around. But what we heard back from you to the survey question down below was you would like some help with planning and roadmap development and with technical and financial case studies. That's exactly what today is all about. And I will assure you, at least once every quarter, we will be revisiting this theme because it is fundamental to where greening healthcare wants to go and where the Canadian society and economy wants to go, and where we believe that most or all of the individual hospitals want to go. So that's where we got to. Before we get to Kitchener-Waterloo, Amandeep, have we provoked or upset anybody enough yet that they're shouting at us?
There's so currently no questions around the low carbon heating plan, but there was one question around the measures that are being implemented by the hospitals, as and how does that kind of relate to the new ASHRAE guidelines around COVID, where they're recommending higher air change rates, or actually higher air change. So I think just if I could address that, that's probably one of the, I mean, we covered that issue in detail in our last webinar, where we had the ASHRAE panel talk about those particular issues. So I kind of personally highly recommend that if you haven't reviewed that webinar, so it's on the Greening Healthcare website, that will address most of those questions around COVID and the ASHRAE recommendations around any of the things that we had a great discussion with the ASHRAE panelists last time.
Yeah, we're really enjoying working with ASHRAE in other building sectors, in schools, and obviously hospitals, and looking now to municipal facilities. This whole question of living with COVID, because it's going to be around, and what modifications do we have to make to particularly our handling systems to be as safe as practical in there. Again, while respecting that that's also where the biggest emissions reductions and energy efficiency improvements are found, within the air handling system. So that again is a great theme that will be with us, we think, for at least another year. So thanks for that. So let's step along to our latest, the most recent case study, again hot off the press. So working with Connie and Kevin and their team at Kitchener-Waterloo. They started, as you know, at the Freeport site. We looked at that one just a moment ago. But Kitchener-Waterloo, what I think we're learning with a fair amount of humility is the principles are the same for each of the hospitals we look at. The application within the unique conditions within those facilities are quite different. So it's not unchallenging, but it's certainly doable. But let's run our way through. If you're not familiar with Kitchener, with the old KW site, the Kitchener-Waterloo Hospital, it's a fairly big hospital. It's an acute care facility. It's got a steam plant, a hot water plant. We'll look at that a bit more closely in a moment. I've mentioned the condensing towers. We'll look at that a bit more closely because, again, that is intriguing to us as a source of readily available heat for our expected new heat recovery chillers. The trigger event here is the hospital's concern that they don't have quite enough cooling capacity in the hottest summer weather. Do I go get an additional chiller to add to the existing plant, or is there a low carbon alternative that I should be considering? So that was the question, that was the trigger event. And again, we've been through this before. Trigger events, in fact, we'll come back to that in just a moment. The trigger events, the key is for every hospital to identify what is the likely next upcoming capital decision I have to make that will prompt me to start down the low carbon path as opposed to the like for like equipment replacement plant. So if you if you're up for this and you've had your coffee, let's run through the specifics there, some of which will apply to your hospitals, others of which will not, but all of which will give you a feel for the kind of things that you'll be looking at within your own site. So the heating plant here, we've got the hot water plant on the left-hand side. Fulton boilers, which are relatively new. In fact, you may recall Greg Donnell giving a case study on Kitchener-Waterloo's tremendous success with energy savings, I think early last year, early in 2019, where they installed these condensing boilers back in those days. They supply hot water. Most of the loads are found down in what's referred to as the lower mechanical room. So that's where most of the heat comes from. On the steam side, look at the boilers first. So we got 3 Miura boilers, which are relatively new. They supply steam in the normal way to domestic hot water, to process equipment, and so on. They also, over time, increasingly steam supplies to where expansions and renovations have taken place. So there are a number of steam to hot water converters in different parts of the hospital that are supplying perimeter heating and reheat. So it's kind of a hybrid steam, hot water, where most of the hot water heating now comes off the hot water boiler plant. The flue gas condensing towers, if you haven't seen those, we may well be profiling them with Fluace and any other suppliers that we find along the way. But the essence of the flue gas condensing tower is they're like a cooling tower. They spray liquid through the flue gases coming off the steam boilers that takes them way below the condensing level, which takes the efficiency up to 100% and beyond. And that low-grade heat, which is typically around 50 degrees Celsius, is available to do whatever can be done. Back in the day, it really didn't have much purpose except for boiler makeup and domestic hot water preheat. A lot more applications in industry, where they have big process water loads, process hot water loads. But when we bring the heat recovery chiller that we'll look at in just a moment into the mix, now suddenly it's a very interesting source of a substantial amount of heat at a grade which you can really pump it up and make good use out of it. So the flue gas, there are 2 towers connected with 2 of these boilers. The third one is not operational, and it generates again around 50 degree heat through the to snow melting, to various other low-grade heat users, and delivers about 50 degrees Celsius flue gases coming out at the other end. So interesting application of a technology that we haven't seen as much as we might be on an ongoing basis. So that is the configuration of the heating plant. The cooling plant, much more conventional. We got 2 big 800-ton train chillers, cooling towers running in there. We've got a couple of small air-cooled chillers in the cancer center. We've got a whole bunch of air-cooled condensers throughout the hospital. We got 1 MRI right now, which is water-cooled, and at the moment is running on city water cooling because of issues with the equipment. Again, nothing unusual here. You may recall Greg's case study again, I think a couple of years ago, where they retrofitted the cancer center for free cooling so that those chillers would not need to run so much in winter, and also connected the cancer center to the central chilled water plant so it could take most of the load during the summer. So this has been part of the success story at Kitchener-Waterloo Hospital in terms of the dramatic energy savings they've seen over time, and configured right now. It is just an efficient conventional plant. So the electricity trends over time have been interesting. So again, if you've been following the Kitchener-Waterloo story, because Greg has spoken on a number of occasions, the blue chart at the top there is since 2013, the electrical savings, which have been getting better and better and better over time, both during the summertime and on the base. And within there, there's, again, we've had case studies from them before, variable frequency drives, a little bit of lighting, a lot of good things that have happened within there. What was interesting is that also brought down the base electrical demand. So these are the monthly billing demands. And you can see during the winter time, they've been coming down steadily. But as we were looking at this one, it's fascinating that the summer demand hasn't come down at all. So there is a suspicion as the hospital puts together the roadmap going forward that in fact the cooling plant, the demand on the cooling plant in peak weather might be higher than it should be, and that could be associated with excessive use of outside air. So one of the considerations they're working with right now is perhaps the summer demand can be, even though they're short of capacity right now, perhaps to improve control and finding areas where there's just too much outside air coming in during hot, humid days, that load can be brought down potentially by a couple of 100 tons. Like, it could be quite significant. So these are the kinds of indicators, if you like, that you can find within any facility to say, how are our loads doing right now? And one of the things that Kitchener-Waterloo is putting in place at the moment is better trend log capability. So all the good things that Jason was describing earlier, they'll have access to, but right now they're only able to work with limited data. So running that through, this is their electrical monthly 2019 numbers. You can see they're running around 2,200, 2,100 kilowatts in winter. So the extra demand in the summer, which is primarily the cooling plant, you can see in July we get to as high as, that extra kilowatts is as high as 93% of the installed cooling plant capacity. So that's one concern. Now, variable frequency drives running harder will be in that number as well, but it confirms the idea that they're pretty tight on capacity right now. The other thing we could look at, because a number of you were good enough to take part in the research we did for the cooling plant best practices guide that we launched, in fact, this year, but we did the analysis earlier. This is tons per 1,000 square feet from a number of acute care hospitals. So North York General with its new plant is around 2.5. Grand River is a bit low at 2.41. But if that was, it wouldn't have to add too much to get in range with some of these other hospitals. And it's not, it's not a big capacity gap, and there's a certain amount of surplus capacity. So we can, for all of you, when you're looking at your cooling plant capacity, let us know what you've got, and we can compare it with this database and say, well, it's in the ballpark, or man, no, you're a bit light, should be looking at more. So again, these are indicators, there's steps along the way to, and again, always with not complete information, because that's the way the world is, but kind of gives you the sense of what's possible, what's practical here. The final piece on the heat, so the heat recovery chiller concept, when that comes together, the heat recovery chiller, you can see, goes in line with the centrifugal chillers. For the summer use, runs through the cooling tower, but the heat is recovered and sent off to reheat systems across the way. Running that through the costs of the two options, whether they're looking at an 800-ton chiller or the 200-ton heat recovery chiller, similar costs and relative benefits that are being evaluated now. That leads to the general idea of low carbon roadmaps. So we're looking for your hospitals to be added to this list as we work our way through. So we end up with this growing directory of hospitals that are working down the roadmap path with their different trigger events and their different plans to address them, and the story unfolding over time, which means your New Year's resolution where we begin, there's work to be done, building foundations, getting trend log archiving in place, getting systems tested, getting your initial vision and roadmap put together, incorporating that in your capital planning, making sure there's lead time to make good decisions, talking to Nadine when they're doing your building condition assessment to help find the trigger events, and making sure you've got your first shovel-ready project for when the carbon funding comes along. So we're going to run up right now a poll. This is just for the hospitals. And we'd ask you to, Michael, you're going to throw that up right now? Just if you could check off the boxes which make sense to you. What are your trigger events over the next 3 to 5 years? And those can be, again, boiler replacement, chiller replacement, local air conditioning units that are in need of replacement. So if you can check off these things, then we can have a sense of where to focus our efforts on the kinds of things that you're going to be dealing with. Do you have direct to drain condensers, which are very expensive? If so, we want to keep water cool, but put them into a heat recovery scheme. Are you going to replace windows, which potentially allows you to lower the perimeter heating water temperature? Do you need to add plant capacity on either the cooling or the heating side? Do you have new medical equipment coming along? So I'm hoping that all the hospitals on the line are checking these things off right now, and we'll feed it back to you in just a moment.
And maybe you could continue with the presentation just because we're getting a bit short on time. And
yeah, we are.
People might have stepped away for a minute from the computer, so just we'll keep that poll up for 2 to 3 minutes.
Okay. So we want to take a look at the technology as well as the methodology, and really happy to have Multistack here today. And gentlemen, if I could kind of bring you in. So Multistack, as you know, is a leading supplier of heat recovery chillers, and we got Mike and Mike here to help us out, and this is how you contact them. And gentlemen, can you bring us into giving the hospitals on the line a sense of what this equipment looks like? You know, let me just throw it to you. You've got great description here, but when they're contemplating the heat recovery chiller installation, what should they expect? You told us how big it is, what it looks like, how it gets configured. Let me pass it over to you if I may.
Good afternoon. Can everyone hear me well?
Yes, we can. Thank you.
Lovely. Thank you. So the genesis of modular heat recovery chillers at Multistack was basically the desire to put a chiller into a very small space, and being faced with the fact that we want to take the chiller apart. So therefore, we're going to make it modular. We can bring it in one bucket of capacity at a time and reassemble it either in the sub-basement or in the penthouse to achieve the desired goal. Somewhere along the way, we discovered that modular chillers actually make hot water rather efficiently. You know, they have a small footprint, really well designed heat exchangers designed for large delta T's and high temperatures. And we woke up one day and said, oh my goodness, we should be recovering heat. And we worked with some consulting engineers that focused on schools, particularly at that time. But we came up with this concept that we would size the modular heat recovery chiller to the simultaneous load. That turns out to be the most efficient approach. But anyway, today, Multistack's revenue stream is about 40% heat recovery, to give you an idea. So that's, you know, $150 million company, US, and 40% of what we do is make hot water, even though we're building chillers. So traditionally, these heat recovery chillers are sized to the simultaneous load, and they're applied in a straddling approach by connecting them in series parallel with the prime mover and the heating system. Now, usually you would not want to have just one module. Normally there would be multiple modules, and the reason for doing that is greater precision of control and redundancy. So an average stack size would be around 4 modules. So if you needed 200 tons, you might not do 2 105s, you might do 4 50-ton modules. So that's just the general approach. We do make heat recovery modules sized from 10 to 165 tons. They range anywhere from 1,000 to 6,000 pounds, depending on size, but ultimately, we combine these things together to satisfy that simultaneous load. One of the new developments in heat recovery today, I think everyone now is probably familiar with the compressor technology made by TurboCore, which gives us no metal-to-metal contact. The bearings actually are magnetic. The shaft of the compressor floats in a magnetic field in about a 10,000th of an inch air gap. And so there's no metal-to-metal contact. That's actually been out now for 18 years, believe it or not. Traditionally, that compressor doesn't handle high lift very well, but there's been development in the last couple of years that enables it to handle high lift. We can do pressure ratios up to 6.5 for those of you in the room who care about those kind of numbers. So the TTH is the new TurboCore version, and though I don't have a picture of it here, we are building chiller modules today with TurboCore magnetic compressors, oil-free, that can do heating temperatures up to 145 degrees Fahrenheit. So,
Mike, I'm just going to step in a couple other points on the modular. Having multiple modules, we also allows us to do variable flow properly. So just a hint for everybody doing heat recovery to make sure that they're set up for variable flow, so you can isolate down to one module to maintain proper delta T's. I've seen that taken out on projects in the past, and they ended up having to put it back in. So that allows you to get wide delta T's at low flows and do variable flow as well.
right.
Yeah, Mike, we understand that each of the modules is kind of standalone, so you have built-in redundancy that one module can fail, but the rest keep marching along. Is that true?
That's correct. And we also have something that's called auto control. So you can retrofit this into a plant with no BAS whatsoever. It simultaneously controls to the smaller of the two loads so that you're not having to run off of safeties. The heat recovery chillers have a bad reputation for not working well from a controls point of view, because the BAS typically had to reset the temperatures on either side to manage the loads, and this does that automatically to maximize your heat recovery and allows you to retrofit the product into an existing system with no BAS intervention at all.
And the key here being that you can get the kind of water temperatures we need to manage an existing hospital in the coldest weather.
Correct.
So how Mike, talk a bit about the configuration. What do we got here?
Yes, so what we have here is a simplified diagram of the way that dedicated heat recovery chillers are typically applied. So you'll hear me refer to the main chiller as the prime mover. So we straddle the prime mover and the heating load. We take a bit of the return water, strip the heat out of it. We wrap it up with the heat of compression and pass that heat off to the heating system. So the question is usually, well, is it in series or is it in parallel? Well, it's in fact both. If you look at the way it's in parallel with the piping, the return piping, but the water is in series with the prime mover. And so the idea there is, and there are a number of different ways to do it, but we feel like that's the best because what it allows you to do is to unload the prime mover, and it actually slides down the unloading curve to a more efficient area of operation. And that can be pretty well proven in operation simulation. Go ahead.
Mike, a couple other points on the heat recovery chillers in general. They can also be used for straight air conditioning. So if you have a peak load issue or you don't have any need for heat recovery or you need redundancy, the heat recovery chiller can be operated as a normal chiller as well. Okay, just
let's go to the last slide quickly.
Mike, I just want to make one other point. If you go back to the previous slide, if you see that's a TurboCore chiller up in the right on the left-hand top corner, that is now available as a kind of a picture of what those heat recovery machines look like. The other reason I wanted to bring that up, sometimes in a larger hospital, we run in Ontario anyway, we run into issues with the Operating Engineers Act because of the kilowatt limit for positive displacement compressors. The TTH, the high lift turbo core machine, is a centrifugal that gets away from any issues with the Operating Engineers Act. So I think this group would be maybe aware of that requirement, so that we'll get rid of that for large tonnage applications.
So the configuration that we were looking at for Kitchener-Waterloo Hospital, that's practical, where it could be working more as a cooling unit in the summer and then work its heart out right through the winter, recovering heat all season long.
Yes, and they could also be set up in a modular capacity so that if your heat recovery load's a lot smaller, you could have one module set up for heat recovery and the chiller larger for the overall cooling load, but then isolate the flow so you get proper delta T's on a smaller part of that modular turbo core chiller or scroll chiller. It doesn't matter. You can do it the same variable flow in either configuration.
Awesome. So other Mike.
So before we go to this slide, is everyone fairly comfortable with the temperatures of water that we can actually heat to? We kind of went quickly over that slide. Do we need to go back to that, or are we good with it? I think we should.
For us, this was the key that made everything possible with existing buildings, and looking at this everywhere now. So we lose coefficient of performance at the higher temperatures, but it gets us through the coldest weather. And then in the spring and the fall, it works its heart out, right?
It can. And what that enables you to do is use existing coils, existing air handlers, if you can get the temperature there, if you're doing comfort heating. I think the important thing is that we can get to those temperatures if we must, but it's still better from a carbon footprint perspective and from an energy usage perspective when we do new design to design around the lower, cooler temperatures. You get the best of both worlds. And today, of course, these are vapor compression refrigeration machines, and so we're limited by the ability of the refrigerants that we have available to us. 410, which is predominant in North America, we can do up to 145 degrees Fahrenheit, 140 degrees Fahrenheit, and then with 134A up to 175. And I don't want to mislead anybody, those are the extreme edges of the envelope. I probably wouldn't design around 175 Fahrenheit. I would back away from that a little bit because buildings, whether they're hospitals or otherwise, are very dynamic. Flow is up and down, temperatures are up and down. If we design too close to the edge, then we wind up with other problems.
And Mike, if we have the chilled water side, in quotes, up around 95 degrees Fahrenheit, how does that help? Because that would be the expectation coming off water cooled condensers around the hospital, maybe coming off heat recovery from the boiler plant. So if we have higher chilled water temperatures, how does that affect how hot we can make the water, or is that not practical at all?
So anytime you can reduce, well, what you're doing by using warmer water, warmer chilled water, is you're reducing the total amount of work that has to be done to achieve any amount of heating, right? So you're reducing lift, or you're reducing pressure ratio, directly reducing work. The important thing is that we are cooling the motors with the suction gas that's coming from that evaporation process. So we have to keep that suction gas cool enough so that we don't have reliability problems with the compressors. So that's one of the reasons why we like to stay on the return side of the chilled water at 50 to 60 degrees, and that gives us the most efficiency as well as the most life on the compressor.
Mike, I could be wrong, but I'm pretty sure if we go with the 134A design, we can go higher than that temperature on the chilled water side. So we've looked at the design. You can go higher temperatures with the 134A design on the suction gas cool. So I know we've looked at designs, I think in the 75, 80, even a little bit higher. So yeah, you can go higher, but you have to use 134A.
Right, and that usually drives the question, well, why don't I just put this on the tower? I'll take the heat off the tower. I can downsize my tower, and that's a better solution. That's not wrong. It's just not the best. And by that I mean BTUs are BTUs, no matter where I salvage them from or recover them from. But if I put it on the chilled water return rather than on the tower, what that does is it allows the machine to unload, and it's worth more to unload than it is to simply reduce load on the tower. And we've done some fairly extensive studies on that. Let's talk about what we have here. And Mike, I'm going to want you to help me with this. This is what we call VME 1.5. It doesn't really matter what VME means. What it really is, it's a derivative of a central station geothermal system that we've been selling for several years. Obviously, most hospitals are not going to be geothermal, and you wouldn't be using that central station geothermal system, but there is a derivative of it that is valuable. That central station geothermal system is really designed to leverage simultaneous load. Heat that it can't use, it usually sends to a geothermal bore field, or heat that it needs but can't get from the load, it usually gets from the geothermal bore field. But let's say we don't have a bore field available. Is that approach still valuable? And the answer is yes, because hospitals are almost always cooling dominant, which means literally I could take all the chilled water that you can ever provide from the heat recovery machines and not really have to worry about it. So these are cooling dominant. So I'm not going to need to put that cold, unused cold water in the ground. So I don't even have to think about that. So I can eliminate valves on the chilled water side that I may have had on that central station geothermal approach. But I keep the valves on the heating side. And what that enables me to do with a modular system is to send heat to the heating load if I need it. And if I don't need it, I send it to the tower or whatever my heat sink is. It could be a tower, it could be a fluid cooler, some other type of heat sink. So this is what we call VME 1.5. Normally it would be called VME 2, but a little play on names there because we eliminate some of the valving. We changed the number. This is something that is very unique and very progressive in the way that it's being done. The only thing to keep in mind, and Mike, you may have some other thoughts on it, but if you're going to reject to the tower, it really needs to be isolated. So when you're laying this out, you need an intermediate heat exchanger between the chiller and the tower.
Yes, correct. And this allows you to do critical cooling as well, because one of the issues if you have a critical cooling application and you have to guarantee that you have chilled water all the time, but if you don't have a heat recovery load for whatever reason, or there's some chance that could ever go down, it allows you to always have cooling by being able to reject out to a fluid cooler or out to the loop through a heat exchanger typically. Just typically in our climate, you're gonna have glycol. So even if you use a fluid cooler, probably gonna have an intermediate heat exchanger on the green side, okay? So that's another option.
Really, really helpful, gentlemen. The Amandeep, any questions from the floor?
No questions.
Let me just remind everybody of how you contact Mike and Mike.